Bang out. hope so.
Good. Okay, so we want to welcome our first speaker is Adam Noonchester. Adam, we've always borrowed talks and backs and forth from GDC. This is a talk that is based on a talk that he gave at GDC this year, and it was one of the best talks that I saw at GDC, and I said we have to get this in front of the AIIDE community. So I'm really happy to have him here. He's going to be talking about the work that he did in Sunset Overdrive. He's been working for Insomniac for over 7 years now. But he was actually originally working for the defense industry and doing some contracting there, but decided that the games industry had a little more interesting stuff to do. Adam is an avid runner, and he's very happy to be here this week. So let's go ahead and welcome Adam.
Thank you. Okay, thank you. As Nathan said, my name is Adam Noonchester, and I was an AI programmer on Sunset Overdrive for the full 3-year development cycle. I worked on most of the normal enemies in the game, and I'd like to take this time to kind of discuss some of the problems that we solved and how we had to use our AI to directly achieve a lot of the design goals of the game. Okay. So this is Sunset Overdrive, and at its core, it's an open-world third-person shooter. It places a heavy emphasis on player agility. We wanted the player to be able to combine over-the-top abilities like air dashing, or bouncing, or wall running, or grinding with kind of over-the-top weapons like a propane tank-powered rocket launcher or a gun that shoots ricocheting vinyl records. And we wanted players to be able to use these weapons to stylishly kill mutants, humans, and other robots. Now, in order for all of this to work, our enemies really needed to do 2 main things. The first thing they needed to do was they needed to force players to actually get up and start traversing. We found very early on from playtesting that if we did not get players to engage with our traversal system from the beginning of the game, then most players would try and play the entire game like a regular third-person shooter, standing on the ground, getting into and out of cover. And so our enemies needed to be so dangerous and overwhelming that players felt like they needed to never be on the ground. The second thing our enemies needed to do was that once the players were up and traversing, the enemies should then test the player's ability to both simultaneously traverse and improvise and fight. The idea was to encourage players to play the game in a fun and stylish manner. And we felt that, for example, bouncing up and down on a car, well, that might be using our traversal system, but it's kind of not fun and boring. And we felt that many players wind up playing games in the most efficient way possible. And so we needed enemies that would make that efficient way be fun and stylish and to have the player keep moving forward and keep engaging with the game. So I'd like to briefly list some of the key ways that Sunset Overdrive is different from a more traditional action shooter like the game we had just made, Resistance 3. This game is a very controlled experience. Not only did we know where the player would enter and exit each setup, but because each space is really only used for one encounter, we could do a lot of custom tailoring to the environment. For example, we could build geometry that exactly matches our enemy's size or their capabilities, or we could limit options that we felt were too easily exploited by the AI or the player. When you contrast that with Sunset Overdrive, on the other hand, it's an open world space in which the player can approach most encounters from nearly any direction. So therefore, we'll need AI that are able to cope with a wide variety of spaces and metrics and that need to play well in spaces that were not even specifically designed for them. Another big difference between Resistance 3 and Sunset Overdrive is that in a game like Resistance 3, both the player and the enemies usually traverse the same space in the same manner. They run around on the ground and they occasionally jump. Wherever the player tries to go, the AI can follow him, and usually by using the exact path that he took to get there. In Sunset Overdrive, our player can bounce on cars, grind on power wires, and do many, many things that enemies can't. And we deliberately chose to allow this in order to make the player feel powerful. However, this does mean that one of our biggest challenges is going to be creating enemies that can handle this asymmetry of maneuverability. So with that in mind, let's start with our most common enemy and kind of the foundation to a lot of our combat. We call this guy the base OD. And since the core of our combat is about traversing and shooting, his primary job is to force the player up onto traversal. And we'll use other enemy classes to challenge him while he's traversing. The base OD attacks by lunging at the player once he gets within about 10 meters. So they've got a lot more range than a normal melee enemy, but they still need to be pretty good at keeping pace. And I'm not really going to talk about a lot of the stuff that you might do to make a normal melee enemy fun to fight, things like hit reacts, deaths, effects, how to tune a lunge. Instead, I'm going to focus on how we made them able to keep pace with the player. And while it may be easy to say that an AI should spread out and attack the player as a group, we found that to do this in an open world while also looking good was much more difficult than we expected, and we already expected it to be hard. This is a fairly typical shot of our game. This is Sunset City. Here's the debug draw for our nav mesh. This obviously represents where enemies can go. One big problem is there isn't nav mesh on any of the traversal elements in this scene, like this rail, wire, umbrella, or car. A similarly big problem is that by simply using a bouncy, that is an object that the player can bounce on, such as a car or an umbrella, the player can move from one section of nav mesh to a completely different section of nav mesh. And in this case, if the player followed this path, then all of the OD might need to go around behind the building and take the stairs, or they might not even be able to chase the player at all. At that point, the player would be free to just stand up on top of the roof, shoot all of the enemy, and suddenly it's our AI's fault that we have a boring game. So in Resistance 3, we had developed a concept that we called nav clues, and we often refer to invisible gameplay markup as clues. Nav clues are just two positions annotated by designers that get stitched into nav mesh and being marked as being connected via a specific action or animation. So in this example, these two green arrows are connected by a 2-meter climb over animation. In Resistance 3, most nav clues were cinematics that would actually be played back exactly as they were animated in Maya. So the enemy or AI would use the position and orientation of the starting arrow as though it were the origin in Maya. Now this looks great, but it's not very flexible, and a lot of Resistance 3's spaces had to be designed to very specific metrics in order for this system to work. And it was immediately obvious to us that if we wanted to cover this city in nav clues that will allow our characters to traverse everywhere, that we were going to have a lot of problems making custom animations that would get them over everything in this shot. For example, we've got cars of different sizes, we've got lots of rails, we've got lots of planters, and we've got lots of jump up and downs, all of varying heights, some with and without rails. And as a further example, here's the nav mesh from the ship game with all of the nav clue connections drawn in purple. Trying to make unique clips for each of these shapes for all of our skeletons, and we have more than 12 different animation skeletons, isn't something that's going to be feasible. We don't want to restrict art or design too much, because that will make our city boring. One of the very first things that we needed to do was find a way to make our AI's traversal flexible enough that the AI can get anywhere that the player can. So we started out by working with our animators to divide our maneuvers up into parts so that we could hopefully mix and match them. For example, to climb over a rail like this, you'd use two animations, an up and then a down. And these are two separate animations that will get stitched together. To climb over a box like this, you'd go up, over, and then down. If the animators make a variety of clips that each begin and end in the same pose, then we should be able to string them together to climb over all kinds of things. For example, this box leading to a drop-down is conceptually the same as the previous. The character climbs up, then the character goes over, and then the character goes down. This allows us to mix and match clips without needing to allows us to mix and match clips and climb over a lot more objects with a lot fewer clips. We broke our traversal maneuvers up into 5 parts. Here in A, you can see the previous climb over. In B, you can see the vault. And in C and D, you have a drop down and a climb up. Now, in addition to the green arrows, we also place a third volume. And we refer to non-rendering cuboids as volumes, and we often use them to define spaces or boundaries. And in this case, we're going to use the size and position of the volume to be able to tell the AI what kind of a thing they're going to be climbing over. For example, from the volume's width, we know the width of the thing that we're going to be climbing over, and this tells us the difference between doing maneuver A and BCD. The volume's height relative to the start and end point tell us how far we'll be climbing, and this really tells us the difference between B and then C and D. In fact, as the character is climbing up and over A, we guarantee that the first clip will scale to end with the character's root joint exactly at the height of the volume's center and exactly at the volume's front face. Similarly, we scale the over clip to end at the back face of the volume. The last clip of the climb over is scaled so that it will land on the ground, but its motion parallel to the ground isn't scaled at all. So while some characters might land here, other characters might land here. The point is that if this volume is properly sized and placed on the object that the character is climbing over, then we have great precision and it looks like the character is actually making contact with the environment. We do similar blending for B, C, and D. There's one other neat thing about our implementation. In our engine, our characters never directly play individual anim clips. Instead, they activate what are called animation drivers. These are basically data-defined blend trees, complete with parameters that can be passed in from code. And this is an example of one of these drivers. The orange nodes on the left are actual animation clips. And these clips all go into a blend node in the middle. This blend node is configured to select an individual animation clip instead of blending two of them together. Now that blend node is set up to use a variable called height that is set from code, and that chooses which of the 7 clips gets selected. Therefore, the output from this driver will be the vault up clip that best matches the height that we'll actually be climbing. And what this allows is for code to operate without having knowledge of what specific heights a character has. We just set parameters in code, activate drivers, and then scale whatever motion comes back from the animation system. Because each driver, or each part of the vault is a separate driver, then the motion is mostly linear in nature, which makes it very easy to scale things in order to get them to look good. And if things look odd because we're scaling things too far, then it's easy to have animators go in and add more clips without programmers needing to mess with code. I had mentioned that there were 5 kinds of maneuvers. The remaining one is jumping, and it isn't all that different from all of the others. We break the jump up into 3 parts, a takeoff, an in-air, and a land. And we then set various variables about the characteristics of the jump, such as the jump height, the jump width, the character's foot state, whether or not their left or right foot is forward, and the character speed as well, and then we activate drivers and work with whatever comes back. The big difference with jumps is that we determine the length of time that the character is going to be in the air and time scale the clip to last exactly that long. This guarantees that the character will have a consistent flight speed and also touch down on the ground on the exact frame that the character's feet touch the ground at the end of the in-air animation. Here's an example of a takeoff driver for use in a jump. In this example, our output comes from a blend node governed by a speed variable. We're selecting between 2 clips plus the results of another blend node. That blend node will select one of 2 clips based on if the character's left or right foot is forward. Essentially, we play a unique appropriate animation if the character is standing still, barely moving, or if they're running, we play an appropriate animation for which foot is forward. Here's an example of selecting between different in-air clips based on the distance that we're jumping. So at this point, our AI is now capable of traversing the world and getting where we want them to go. So the obvious question is, where do we want them to go? Remember that we have a very fast and agile player, and our goal is to have AI that can keep the pressure on the player. We had initially started by just having all the base OD go to the closest point on nav mesh to the player's current position. Now, this had all kinds of problems, and the closest point on nav could be on a bridge above you. It could be on a roof that you happen to be going by, or if you're on a car, as you're bouncing on the car, it could easily move from the front of the car to the back of the car. And in order to solve this problem, and a lot of the other base OD problems that we ran into, we had to have a little bit of a shift in our thinking. Up until this point, we'd been thinking about all of the base OD at sort of an individual agent level. Each base OD would try and figure out the best thing to do, and then he'd go and do it. The problem is that the best spot or the best thing to do changes very, very quickly, and it's incredibly hard to predict with any amount of accuracy. So if all the base OD are trying to predict the same perfect spot, then they will all make the same mistake when our prediction is wrong. What we want is just one of them to be frequently in a good position. And the easiest way to do that is to use our high enemy count to try and get guys to potentially interesting positions. To put it another way, we want to try and calculate as many interesting places to be, paths to take, or things to do for all of the base OD instead of having all of them try and decide on their own. With that in mind, we developed something that we called a nav position tracker. This will simultaneously track several different kinds of positions, shown here by a bunch of debug spheres. We'll track the actual closest point on nav to the player, the closest point on nav to the ground position below the player, and then the closest position on nav to several points offset from the player. And now the way this works is that each base OD is given the position that is currently closest to him, and he goes there. Since the base OD should be spread out, this usually means that you'll have different guys trying to go to different positions. Without the tracker, in a case like this, you'd wind up with base OD rapidly orbiting the car as the position changes from one side to the other. Go ahead and play. All right. So without the position tracker in a case like this, when the character changes direction, the closest point on nav would flip from one side of the railing to the other, which would cause the base OD to think they either need to run around the railing or jump over it. Now, since there are positions on both sides, I don't have that problem. So as an additional example, here you can see that as I grind along, there's always a position on the ground below me. But as I go by buildings, sometimes positions pop up to the top of them. Now, this is great because it allows any enemies on the ground to continue chasing me from there, but enemies in other positions may decide to try and get up on top of buildings to chase me, which is great if I happen to just decide to jump off. So now we were at the point where our AI could chase the player, but it wasn't enough. As you can see, they tend to kind of clump up, or in other cases, they'll conga line once they've been chasing the player for just a little while. So while they're technically fulfilling their purpose of chase the player around and hit him, our AI is still the root of boring, repetitive gameplay. We need to get the base OD to spread out. This will make our combat more dynamic and challenging, and it will make our enemies feel more lethal and intelligent. We started trying to solve this problem using a technique from our Ratchet and Clank games called arc angles. An enemy approaching the player with an arc angle of 0 will run straight at him, while one approaching with an arc angle of theta will take the top path, negative theta being the bottom path. All of these arc angles are managed by a flanking manager that exists on the player. It assigns out angles to approach to each of the base OD so that we don't have all of our enemies trying to approach from the same direction. And this actually works really great when we're near the player. Here you can see the same mob of base OD using arc angles. You'll notice that they immediately begin to spread out, and I have to do a lot more work to avoid being hit. At a low level, arc angles work by changing the position that an AI is trying to nav to. As the base OD or the player moves, we recalculate the position along the arc angle and try and go there. In order to prevent arc angles from potentially sending a character to the wrong side of a wall, we require that a line from the target, the player's position, to the arc angle position be unobstructed on nav mesh. In practice, this means that because our levels aren't flat, empty planes like this, the arc angle destination is usually within about 5 to 10 meters of the player. And this has the unfortunate effect that groups of enemies that are far away from their target will have their paths only vary over the last couple of segments. We needed to find other solutions for getting base OD to spread out when they were far from their target. Our first idea was to go in and make all of the polys involved in nav path queries more expensive so that subsequent path queries by other characters would be likely to find an alternate route. Now, this didn't work. As you can see here, the size and shape of nav polys doesn't necessarily correspond to features in the world. Right here, we've just got a bunch of polys coming together in the middle of the road. And here we've got this thin sliver of a triangle sandwiched between two large triangles. This inconsistency can cause weird things to happen. Say we have one character move along this path, and this would add cost to these polys. This will sometimes have very little effect on a path starting at a nearby position, which isn't great. Worse off, if we move both of the path start and end points down just a little, well then this becomes the lowest cost path. What we needed to find were ways to add cost in places that didn't have awkward knock-on effects like this. One further problem that we had with directly weighting the nav mesh that I feel is worth mentioning is that we were unable to figure out a good way to efficiently store, utilize, and access all of this data. We have an 8-player multiplayer mode, and we have some very large multi-faction, multi-target fights. Instead of that, the first thing we did was added cost to individual nav clues. Here you'll see a bunch of characters trying to get from one side of the fence to the other. And you'll see purple lines begin to stack up as the nav clue's cost gets changed. As you've seen before, our world's incredibly dense with nav clues, and this makes adding weight to them meaningful. Additionally, since they correspond to actual visible geometry and are usually near the edge of, or near the boundaries of nav mesh, they don't cause the other awkward problems that adding weight to nav polys does. Seeing one character jump over a car while another runs around it isn't a particularly awkward thing. Basically, if a bot gets a path that goes through a nav clue, he'll increase the cost of using that clue so that subsequent path queries are likely to find another path. As an additional layer, bots who get near a clue that is already in use will try to immediately find an alternate path. This is what causes the cost to kind of go up and down here in this video. Adding cost to nav clues combined with arc angles still wasn't quite enough because there were still times where an AI could get a path that went for a long distance without going through any nav clues. And so enter what we called influence spheres. These are something that our engine group gave us, and it's basically the ability to bundle a bunch of spheres along with a path query and associated costs. Here you can see 4 such spheres drawn in red. And as an example, the one on the bottom sphere will make crossing that area more expensive, but only for one particular path query. And the way we utilize these is that when each base OD asks for a path, which is fairly frequently, he will ask the flanking manager that I mentioned before, the guy who manages all of the arc angles, and it will actually look at all of the paths that all of the base OD targeting a single player are using and look for common close bend points. And it will then place these influence spheres on those bend points to try and force the guys to find an alternate route. This works well because path bend points will correspond with features of the geometry. If they didn't, then path smoothing would have removed them. We also try and keep the size of these influence spheres relatively small so that if they don't result in a substantively different path, smoothing will be able to kind of iron things out and it won't look like the character is just running around empty space. So around this point, we felt like we had done a lot to the base OD to make them dangerous and fun when the player is close to the ground. They spread out, they surround you, and they do a pretty good job of killing you. And this really encourages our core gameplay. However, if you get up high, it's kind of trivially easy to just move back and forth and murder them without any resistance. And while they're supposed to be vulnerable to traversal, at this point, it just felt like traversal was a win button, and the game was quickly becoming boring. So our AI was still causing problems, and our last goal was to get the base OD to occasionally become a threat to a player who is traversing well. This isn't something that we needed to have happen all the time, but it's something that we needed to avoid the player going into kind of autopilot. So our proposed solution was to try and get base OD perched up on individual traversal pieces that the player is probably going to use. If the player happens to get too close to the individual guy, the guy will try and hit the player. In order to figure out what traversal to use, we actually collect all pieces of traversal near the player and then score them on a number of factors. Every time the player uses a given piece of traversal, we make it tastier. And this is very important because the key thing that we're trying to encourage is the player to sort of keep up their forward momentum and movement. We don't want them to be able to use the same grind or bouncy over and over. The second is that we predict, using Dead Reckoning, the area that the player will be in for about the next second or so and make traversal in that area more attractive. Finally, we factor in how close each individual base OD is to each piece of traversal. Here you'll see that as I traverse up onto wires, there'll be a bunch of boxes that appear. These are potential places for base OD to wait for me. Base OD can wait on bouncies, they can perch on top of grinds, or they can hang from grinds. The lines going down to the ground correspond to nav and collision tests that we use to validate jump-up positions. We also restrict them so that no more than 25% of the group can be waiting on traversal at any one time. I also feel that it's worth mentioning that we turn on this ability as well as many other base OD abilities gradually from the beginning of the game. At the beginning of the game, they never get on traversal, don't lunge at the player, and are much nicer in order to sort of ease the player into our frenetic mechanics. I think it's worth putting it all together and taking a look at how all of these systems interact with an encounter with base OD late in the game. Now, you can see that they're already starting to spread out. And there are guys using our vaults to get over the trucks. Here's a guy perching on traversal that's about to hit me. We have another guy use this car to jump over me, or to use a jump to get over the car. And guys are really spread out now. And I have to go through a lot of effort to avoid getting mobbed as soon as I come back down to the ground. And this is great because this really encourages our kind of core gameplay of traversing and fighting at the same time. Now, another thing to notice is that as I get up on top of this roof, I'm going to come down, and you'll be able to see clue weighting working because I'll have a big clump of guys after me who all take kind of different paths down off of the roof. Here they all come. And another thing to notice is that I really start fighting back now, and these guys go down pretty easily, but about here I've taken out about a quarter to a third of their number, but their ability to chase me and to kind of force me to keep reacting, to keep improvising, like it stays high. And a good side effect of having enemies that are this aggressive or this capable of chasing the player is that we don't really have the problem at the end of an encounter where the player needs to hunt down kind of the one last straggler. Everything comes to the player, and the fight kind of just wraps up when it feels like it, or feels like it should. So let's move on to some of the problems that we faced with ranged enemies. These are our three kind of core shooter classes. The guy on the left, we call the blower. He lobs green projectiles at his target. The guy in the middle is the Physco rifle bot. He has a plasma rifle that shoots very slow-moving but very high-damage shots. On the right, we have what we call the scab shooter. He's basically a post-apocalyptic jerk with an AK. The biggest thing with ranged enemies is where they choose to fight from. We could obviously have them just kind of chase the player, but that would make them feel like cheap, boring versions of the melee class. So what we want is for our ranged enemies to maneuver to interesting vantage points and engage the player from there. In our previous games, we do this with something that we called fire points. These are usually fixed positions, oftentimes annotated by designers, that are suitable for an AI to shoot from. And oftentimes they're suitable for an AI to take cover behind. And in that case, they have a direction associated with them. Here's an example of what common fire point markup would look like in our editor. This fire point could be used to roll out to either the left or the right and shoot at targets. And then during combat, bots will kind of gather all nearby fire points and then try and score them based on a bunch of criteria like proximity to target, does it provide line of sight, that kind of stuff. And we actually started using fire points and cover with all of our enemies in Sunset Overdrive. And we ran into several problems related to both the speed of our players' traversal as well as the open nature of the game. You see, Getting into and out of cover is actually pretty slow, and this made the enemies look really unresponsive and dumb because they would get flanked and they'd take just a little bit too long to roll back into cover or roll out of cover or change cover. It also felt unfair to some players that enemies could use objects in a way that they couldn't. And finally, proper cover usage is heavily angle dependent. You don't want to use a piece of cover that will kind of point your back at the enemy. And given how fast our player moves, what fire points are valid could change very, very quickly. And we actually tried to make this work for a little while. We added more fire points, and we even went so far as to just say, hey, there are fire points everywhere on a 1-meter grid, and to hopefully give our characters options to compensate. But this actually only made things worse, because it would cause enemies to kind of bunch up with guys using lots of nearby fire point, or lots of guys using nearby fire points, or a single character could kind of dither between 2 nearby fire points. And trying to compensate for all of these different things that we didn't want to happen was causing our evaluation, our scoring function, to go out of control. We were trying to tune a formula that would take into account the angle that the angle of a fire point. Does it point at our target? Does it actually provide cover? Does it actually provide line of sight? Is it too close to any of our friends? Is it too close to any of our enemies? Is it close enough to our ideal range? Is it close enough to where the designer wants us to be fighting from? How dangerous do we think it is? Is it too close to our current fire point, or does it happen to be too far away? And this had become a very complex function that had become very noisy. And this noise led to inconsistent behavior. And this is really bad because it makes the AI appear to act randomly, which causes them to be perceived as either being stupid or unfair. We came up with 2 alternative solutions for our enemies. The first one is perches. These are elevated positions that bots can take and then jump between. We'd used them with our long leg enemy class on Resistance 3, and despite being somewhat similar to fire points, they offer some big advantages. The first is that they're omnidirectional, which makes evaluating them a lot simpler. The second is that there usually aren't very many objects suitable for perching on in a given scene, which makes scoring even simpler still. The third advantage is that they separate the character from the ground and usually cause them to be silhouetted against the sky. This was especially important for this guy because prior to using perches, he was on the ground mixed in with all of the other base OD, and you could never find the guy that was shooting at you. The final thing is that jumping between perches not only looks cool, but if an enemy does it in response to being shot at, it's almost as effective as taking cover. However, we still wanted our enemies to be able to use the environment to shield themselves. We felt that this would give some variety to our enemies, encourage the player to move around a bit, and add a different kind of rhythm to combat that would make our human enemies feel more natural. And around this time, we were focusing on the layout of simple spaces that we felt the player could approach from multiple directions. And our inspiration was a scenario similar to this. If you can imagine that this is a top-down view of a space and the circles kind of correspond to pillars or trees or some big objects. The general idea was that you have the player who might be fighting some enemies in this kind of mix of tall occluders. Now, as the player in like a deathmatch game, you might just move slightly to the left or the right to kind of fall into the shadow of one of these and take cover behind it. In our fire point-based solution, you might place 4 or 8 positions around each of these to let the AI choose from them. And then you've got a world that kind of looks like this to the AI. And so hopefully you can see why it's a little bit confusing or difficult to have a scoring function that can consistently decide on a best location. And things get even worse when you have multiple enemies. Our solution was to stop pointing out the places to stand and instead point out the objects to use and dynamically figure out where to stand and how to fight. Imagine that the green circle is our target and we want to use either the circle or square-shaped object to attack them. If we draw tangent lines from our target in green to our box and circle, you can see that these lines define a gray occluded area. We can easily calculate the tangent positions as well as vectors, and from those we can construct everything else that we're going to need. If we move back from the tangent point and then rotate inwards, we can easily calculate a spot that is just inside the occluded space and thus hidden. Similarly, if we rotate outwards, we can calculate a good spot that is just barely visible to fire from. Stepping between these 2 points allows us to move from occluded to not occluded, and as the green circle, that is our target, moves, we can easily recalculate these tangent lines and get new in-cover and out-of-cover positions. We can also perform raycasts or nav checks between any of these positions to do validation at runtime in order to make things more robust. Here's a video of a scabbed shooter using some occlusion. He's going to step out and shoot at me, and then he's going to reposition to a different piece of occlusion. Now, in Sunset Overdrive, we force our AI to change occlusion on a regular basis in order to keep things active. I'm going to turn on the debug display in a second, and you'll see a bunch of red and green lines. These correspond to raycasts that we do at runtime to verify whether or not we can see the player from the out-of-cover position and whether or not he can see us from the in-cover position. Each of these large objects is a single piece of occlusion. And since there are fewer of them than there would be in like a firepoint-based solution, we don't have odd scoring factors that exist solely to keep guys from bunching up. Here you can see that as I move around, all of these positions get recalculated. And because of this, we don't really need to consider direction when thinking about what piece of occlusion to use, since any of these objects could be used to fight against any other position. In fact, our scoring functions really only need to consider 3 things: line of sight, distance to target, and proximity to where the designer would like us to be. These are, in fact, the same 3 things that PERT scoring cares about. Now, this kind of occlusion works really well for fighting a target that's about on your level or kind of above you. But when you've got a target who is below you, oftentimes the ground that you're standing on prevents you from firing at your target. And oftentimes moving down to your target's level to re-engage them isn't desirable. And so we effectively needed to find a way to get our enemies to use the edges of buildings as cover. The concept is mostly the same. Here's a side view, and we want to use the front-facing edge of this building to attack our target. A tangent line from our target through the building edge defines an occluded area. If we take our height into consideration, we can easily find a place to stand, and then stepping forward will give us a place to shoot from. This gives us our 2 positions to move to, or move between. In practice, this is what it looks like to the player. The enemy steps forward and is now able to shoot at his target. He is then able to step back and become occluded. We call this line occlusion because it's generated in the city by marked up lines used by the player to know where they can pull themselves up or grind on things. Here's a view from above. The blue spheres are the tangent positions. The yellow, the out of cover, and the red are in cover positions. As another note, our bots really only begin looking for this kind of occlusion once they determine that normal cylinder and box occlusion will not allow them to fire at their target. So at this point, we had ranged enemies that were capable of moving between interesting locations and effectively engaging our player. But we started getting a lot of feedback about the game feeling very chaotic, very unfair, and extremely frustrating when fighting ranged enemies. You see, the problem was that it wasn't clear to the player what the enemies were doing and why. And in particular, it wasn't clear what the player needed to do to avoid being hit. We were asking the player to continuously traverse, and then we would punish them for doing just that. Players would oftentimes find themselves in situations with either the blowers, scab shooters, or physical rifle bots where there were bullets everywhere at seemingly random times, and they had no idea what to do about it. We didn't want players to feel like they had to fall back on regular cover-based shooting mechanics, and so we needed to change our AI so that they better challenged but not punished players that were playing the game. We started trying to address our blower problem the way we usually handle lob or mortar style attacks. We kind of draw some reticles on the ground. But as you can see here, there's often too many of them, and they will kind of appear at random, and so it's not clear exactly what you need to do. We also tried reducing the amount the blowers fired or prohibiting them from firing if there are too many shots already in the air, but this made them feel impotent or dumb because you'd wind up with a guy on screen aiming at you who was not allowed to fire. It also had a negative effect on difficulty since increasing enemy count beyond a certain point did nothing to difficulty. What we decided to do was to manage all of the blower shots versus a single target as a group. The idea was that individual guys could then coordinate their shots, and they could draw out patterns on the ground that would hopefully make it clear to the player what they need to do to avoid being hit. We prototyped several patterns, but kind of wound up with this line sort of pattern, and then sort of a circle fill pattern, at least when the player's on the ground. And the neat thing about having a kind of a geometric pattern like this is that it's easy to take it and make it a little bit bigger or smaller based on the number of guys that are participating. This allows all of the guys to keep firing, and it makes the pattern a little bit more dangerous, but at the same time doesn't make it harder for the player to parse what's going on. In order to prevent the player from becoming overwhelmed, we space out our barrages by about a second. And in between every 2 to 4 barrages, we'll wait an extra long time of about 4 to 5 seconds. Now, when the player is traversing, we walk the grind wires in the same way that the player character would move without any stick input. This means that if the player doesn't change course, they're guaranteed to be hit. Additionally, it's worth noting that all of this kind of group targeting gets turned off if the player decides to charge an individual blower. At that point, that individual is allowed to shoot at the player as often and as accurately as he can. Now, our other 2 ranged classes fire straight line projectiles, and so they needed a different solution since they couldn't really draw out patterns on the ground. We started by looking at some of the solutions that we'd employed from past games. For example, in Ratchet and Clank, off-screen enemies will oftentimes try and deliberately miss. In Resistance, guys who are off-screen will try to fire a volley in front of the camera before becoming more accurate, and we came up with some solutions for sort of nerfing our enemies' accuracy based on our experience from those games. The first was that we said on-screen enemies who are within some distance threshold should try and be accurate. The second was that enemies outside of this distance threshold should try and not be accurate. Enemies who are off-screen inside of their distance threshold, but not too close, should try and fire a volley in front of the camera before becoming accurate. The fourth was that close enemies, regardless of if they're on-screen or off-screen, should always be accurate. And we added this rule because the majority of the time the player knew the enemy was there, usually because the player had deliberately turned their back on them, and it felt really dumb to have the AI deliberately miss at that close range. We added a 5th and final rule on top of this, kind of a fall-through. One character should always be accurate, so even if everybody is far away or everybody is off-screen, one character should be accurate and threatening. And this all worked really great until we started playing the game. You see, our scabs use hit-scan bullets. This means that the bullets will hit the target the frame they're fired. These rules work okay when the player is on the ground because that kind of forces them to react and get up onto traversal. However, just allowing them to be accurate because they happen to be in range is far too punitive. What we wanted was for our AI to encourage the player to stay in motion. First, we decided that the scab should shoot the player if he used the same bouncy too many times in a row. Here I'm changing bouncies and they don't hit me, but as I stay on this same car, they suddenly start to be able to shoot me. Now I'm going to start moving again and they're going to immediately kind of lose me. And as I come back around here, I'm going to use this same car too many times and they're going to start hitting me again. The other case that we needed to handle was what to do while the player was on grinds. We wanted to discourage players from finding like a really tiny loop or just kind of going back and forth in the same spot on a grind. So we decided to track how much the player is moving by periodically dropping breadcrumbs. Here you can see the player going around in a large circle. Here is that same circle from above. I've turned on the debug display for our breadcrumbing. We try and drop one of these spheres roughly every half second, and we then track how long the player is in each sphere. If the player stays in any one sphere for too long, well then he's considered not moving. Whenever we try and drop a new sphere, we delete the oldest one, or we delete the oldest one that the player is not in. If none exists, then we don't create a new sphere. Again, here's what it looks like from the player's perspective. I've disabled the debug display because it makes things impossible to see. While I'm grinding forward, I don't stay in any one of these spheres for too long, which is fine because it really encourages our core gameplay of traversing and shooting. But as I come back around here, I'm going to start going back and forth, and those timers are going to start ticking up, and then I'm going to start getting shot. Now, we increase the speed that scabs become accurate over the course of the campaign. This applies to both the number of times you can use the same bouncy, as well as the amount that you need to keep moving while on grinds. They're actually very, very, very forgiving at the very beginning of the game. Now, I'd mentioned before that our Physco shooters fire slow-moving shots. Our kind of 5 rules on accuracy work well on the ground, but the scab solutions that I just showed you don't work very well for when the player is traversing. Because since the shots move slowly, you'll wind up with this unparsable hail of bullets, regardless of if they're deliberately trying to hit you or deliberately trying to miss you. Instead, we decided that they should use their bullets to sort of create hazards in front of the player. If their target is on a bouncy, they're going to try and predict where their target will land and fire all of their shots there. The idea is to create a hazard that the player needs to respond to. If their target is on a grind, they'll choose a point ahead on the grind and fire all of their shots in a single volley through a single point. Again, we're trying to create a hazard that makes the player react. Because all of the bullets go through one spot in a straight line, it's much easier for the player to recognize what is going on and what they need to do to avoid being hit. I want to mention one final problem that we always run into with ranged enemies. In the previous videos on occlusion and perches, you've seen enemies repositioning very frequently. And this is actually really great if there's 1 or 2 enemies, because it makes them feel very aggressive and dynamic. However, in larger battles, when you've got 3, 4, 5, or 6 enemies, if they're all constantly repositioning, then you're just going to overwhelm the player. The player will stop being able to parse what's going on. They'll lose situational awareness of where things are on the battlefield, and then everything starts to feel very random and very frustrating. It's not a hard thing to do, but limiting the total number of shooters in motion can have a huge effect on how readable your combat is. If you can bias this towards only letting guys who are on screen move, then that's even better. Now, our enemies were already organized into squads for other reasons, so we kind of piggybacked on top of this and said that they're allowed to switch markup if no other markup using enemy class in their squad is currently in motion, if they're being actively damaged, or if they feel the player is rushing them. So I'd like to talk about some of the things that I've learned and some of the things that I think that we need to do differently and look into moving forward. Sunset Overdrive is by far the most complicated game that we've ever made. This talk has only touched on a very small fraction of all of the systems that drive AI behavior. This makes testing both really important and really hard. I should have had our QA team using some of the more simple test levels that you've seen footage from here today in order to test core AI features. Instead, our QA team spent most of their time focused on playing the shipping game. As an example, it's very hard to notice when something subtle, like nav clue waiting, breaks in the shipping game. Nothing crashes, levels don't become, or missions don't become uncompletable, there aren't asserts, and enemies can continue to chase the player, but you do get enemies kind of queuing up at these traversal elements, and things get a lot easier and a bit less fun. And during optimization, we had some bugs creep in, and our nav clue waiting was completely busted in both the review build and the build that we sent out to early YouTube streamers. A lot of the early feedback I felt mentioned the fact that the game looked kind of easy, and I think this was actually a large part of it. Had I just asked someone in QA, hey, load this checkpoint in this test level once a week, make sure that they divide up into 3 lines, then this wouldn't have happened. Another thing that I think we need to look at improving is the customizability of our path queries. Right now, most of our time on working on NavMesh was spent reworking and optimizing our queries as well as our storage to handle the massive increase in size of our world. The queries are pretty straightforward. You pass in a pair of endpoints, some influence spheres, and then you get back a shortest path. However, I think it would be nice to be able to kind of customize these and find non-shortest paths. In particular, I'd like to experiment with pathfinding that understands arc angles, or using the nav mesh to search out and find nearby occlusion, perches, or other kinds of markup. Speaking of markup, we have prefabs similar to Unity, but those didn't work very well for any of the nav clues that we needed to place. Because if you put nav clues inside of a prefab, that doesn't necessarily, like take a rail for example, if you put nav clues inside of a rail, you don't know if that rail is on the ground, or you don't know if some artist happened to put like a lamppost right in the middle of that rail at some later pass. So we didn't have the programmer time to actually go through and modify the builders or do kind of any offline checking to make sure that all nav clues and prefabs were valid. And so our designers had to go through and hand place nearly every single nav clue in the entire world. And this was an incredible drain on them, and it's something that we really need to look for more solutions to in the future. And I'll leave you with a couple last 3 pieces of general advice about creating enemies, particularly for an action game. And these are things that I constantly came back to while working on Sunset Overdrive. The first is that you don't need to be using kind of advanced group tactics or doing some kind of a military sim to benefit from thinking about things at a macro level. Don't shy away from components or systems that try and do things that are group focused. Even if what you're solving doesn't seem to be a group tactics problem, it's often really, really useful to be able to think about combat as a singular, holistic whole. If a player can't parse what an AI is doing, that AI is never going to be fun to fight. In a test level with one enemy, it needs to be immediately obvious what that enemy is doing, both through their visual and audio cues, both on-screen, when that enemy is both on-screen and off-screen. This also means that they need to stand out from the background and from each other. You need to pay close attention to enemy silhouettes and where in the environment they'll be. For example, in Sunset Overdrive, we partitioned up a lot of our enemies based on where they would be. We have a class called muggers that stick mostly to walls. Our blowers stick on perches. A class called the wingers fly up in the sky. The regular base OD are tiny on the ground, and this big guy, the Herker, is on the ground, but he's much, much bigger than everyone else. The final and I think most important piece of advice is focus on testing player abilities. Don't just design enemies that do something cool. Figure out what kind of response you're trying to get from your player. Figure out what kind of a role does this enemy play in the combat in your game. How do you want combat versus them to play out? How are the answers to these questions different for all of your enemies? If you don't do this, then your combat will likely be kind of visually diverse, but from a mechanics and gameplay point of view, it's going to be very monotonous and not as good as it should be. So with that, I'd just like to thank the following people for reviewing this presentation. And I don't know if we have time for...
Yep.
OK, if there's time for questions. Thank you. OK, we've got about 5 minutes.
Yeah, you mentioned there's a lot of issues with confusion among the players.
Yeah.
How much of that do you think can be solved by designing a few good tutorials? On the other hand, you don't want to give everything away, explain everything, like this is how the monster is going to behave, because that's kind of give everything away.
Tutorials are definitely a big part of it. However, a lot of this confusion was stuff happening with us, like internal to the studio. Like we've been playing this game for 1.5 years, and we still get confused, and we still don't know what's going on. And if people that are working on the game are finding it too hard and too frustrating, that's a real quick sign that something needs to change.
Were you able to use any AI in your QA, like maybe a computer-guided player to test things like queuing up that clues and stuff?
We provided kind of things in the debug menu that QA could use to sort of like tell an AI to go to a specific spot or to sort of debug what was going on in the AI. We unfortunately haven't ever really looked into using something like AI to search for holes in collision, and I think that's something that would be useful going forward. It's just not something we've ever had in this time in the schedule to implement.
Yeah, related to that, are you able to do much in the way of automated testing of, the overall AI, or are you really relying on humans in QA to just beat on the system?
We really are relying on humans in QA to beat on the system. We could probably write some unit tests for like the very core parts of the system, like, hey, does the behavior tree system do what it's supposed to? Does pathfinding find the paths that it's supposed to? But a lot of this is so very subjective that I'm kind of struggle to see how you could automate some of that.
What was really interesting in your talk was that you learned that you need to provide to the players some sort of cognitive patterns.
Yeah.
My question, I guess, is should AI programmers take a primer in cognitive psychology, or do you want to basically have the QA come back to you? And how can you do that early on? Like then you have the you need to basically make the levels and everything else before you get that feedback and change.
Yeah, so I do think that it's very valuable for an AI programmer, any gameplay programmer, to kind of be able to get in the headspace of one of their players. And that doesn't necessarily have to be through psychology. I got a lot of it by just being very interested in game design in general. And as an AI programmer, I think it's good to have kind of a good feel for what the direction that the design of your game is going in. As to kind of the second part of your comment, we do, as we're starting out trying to build enemies, we do often place them in test levels or try and come up with test setups to sort of play and verify that their behavior is kind of working how we expect. And we'll build a space and we're like, okay, we think this is an ideal space to fight this enemy. And if we put him in there and it sucks, then we know that, okay, either we need to change the design of this enemy, or we need to rethink how we're communicating what he does, or maybe like he's just good for some different kind of space or different kind of mission.
So you were talking about tweaking the AI to make the game more interesting.
Yeah.
So what happens when in multiplayer deathmatch, do you do any tweakings to make the gameplay more interesting?
In multiplayer, so our AI, the different factions, like the base OD or the scab shooters, they'll all fight each other, so they all already have to understand the concept of multiple targets. And there are actually very few places in our AI where we specifically think about what is the player doing. We think about what is my target doing. So there wasn't really anything specific at the AI level that we had to do for multiplayer. Like there was a lot of work for how do we sync 100 guys over crappy network connections, and there was a decent amount of kind of knobs that we gave to the designers to allow them to tweak different things for multiplayer, like how quickly do guys become accurate is different in multiplayer versus the campaign, or how many guys can be shooting simultaneously, things like that. Okay, sure.
You showed that sort of open world where the enemies were chasing you at a test level.
Yeah.
How quickly did you usually go from an idea that worked in that test level to like in the more complicated situations in the game?
That's kind of different for every enemy class. It was a 3-year production, and we started working on like the base OD and the human shooter class from basically the beginning, and we didn't really have our open world in any kind of built level until probably a year and a half into production. So they got a lot of work in test levels, as well as setups that designers would kind of come up with. For a lot of our later enemy classes that came online more towards the end of production, it would be very quick from, all right, a programmer, me, or one of the other guys has a test level, we get this guy functioning in the test level, verify that he works, and then get him to a designer to have him hopefully placed in the level within the week.
You said that the enemies fight each other, but a lot of the stuff that you've been talking about seems very specific to a player, right? It wouldn't necessarily work when two enemies are fighting each other. Did you have to do different things for AI on AI battles?
There were a couple of times where we'll kind of cheat things a little bit, where where, like for example, a lot of the predictive targeting that we'll do versus a player, we will not do versus other AI, or we'll just shoot directly where we know the AI is going to be. But a lot of it is mostly just stuff that gets turned off when the target isn't a player, because the AI can't grind, the AI doesn't bounce. So it's actually simpler.
Okay, this is the time we have. I'm sure Adam would be willing to answer questions later. But
Yeah,
let's
sure.
thank him one more time.
Thank you.
And we do have a coffee break now, and then the next session will start at 10:30. So we'll see you back there at 10:30.
Oh, yeah.
I really enjoyed your talk. I watched most of it through the laptop. I apologize.
Okay, that's fine.
But,
That's fine.
How's Martin looking over people's heads anyway?